It's okay. Oh, okay, now I get it. Okay, perfect. Okay, so now I will introduce the concept of quasi-normal modes, which are a nice way to model what happens when we perturb, let's say, black hole geometry. So what happens if there is a perturbation here due to the merging of two black holes? What happens is that this perturbation will leak out into infinity, so it will die out at infinity, and then it will leak inside the horizon, and we will lose a trace of it. So what I will do is to explain the mathematics behind this concept, and I will start with the simple case of the Schwarzschild black hole. So probably most of you already know the matrix for the Schwarzschild black hole, which is simply this. The sine theta squared of, let's say, the phi squared. Okay, where f is of the distance, y minus 2m over r, and we set g Newton equal to c equal to 1. Okay, so now what we want to study are the simplest perturbations, which are the scalar perturbations in this background, and they will be described by a box of a function capital phi of the coordinates equal to 0. And we make the following ansatz for the wave function. So e to the minus I omega t times a function psi of r, and also y of theta and in principle phi, the coordinate phi. Okay, so I mean, you already know this probably. Minus g, the derivative with respect to mu of the square root of minus g nu nu, the nu phi. Okay, now this differential equation for the case of the Schwarzschild black hole and many other geometries can be separated into a radial differential equation defined by a potential, which is the Regge-Wheeler potential for the scalar perturbation. And then also, let me use the notation. Okay, here s theta is sine of theta, just to be precise. So s theta with respect to theta, again, s theta with respect to theta of y minus m phi squared where k is the separation constant we introduced in order to separate the differential equations, while m phi is the, so I mean, let's say that this should be, we can take the following ansatz, m theta minus m phi phi, and then we have and then PL of theta. Okay, so basically this is the differential equation for the spherical harmonics. So we already know that the separation constant k in this spherically symmetric case of the Schwarzschild black hole, it's L times L plus 1, where L is the total angular momentum, the quantum number related to the total angular momentum. Okay, now, as you can see here, this prefactor here, containing the second order derivative, if we perform the change of variables which is basically the tortoise coordinates, if we perform this change of variables, this differential equation is automatically brought into the canonical form with the Regge-Wheeler now computed at some R of x, given by this, inverting this relation, which is a little bit more complex, but okay. So now, this potential is very complicated. So what we can do is to study a simpler potential. So we replace the Regge-Wheeler potential. We replace it with, sorry, this is a function of x. We replace it with another potential called the Poisson-Teller potential. Which is very similar and is defined by this function here. It's basically V0 divided by the hyperbolic cosine squared of this alpha times x minus x0. Okay, so the nice feature of this tortuous coordinate, aside from bringing the differential equation into canonical form, is that they map the interesting locations here. So we're interested into infinity and the horizon. So when r goes to infinity, we still have x that goes to infinity. Whereas when r goes to the horizon, which you can see here, is the location of the singularity. So the horizon RH is equal to 2m. From this change of coordinates, you can see that when, sorry, there is a plus here. When r goes to 2m, x goes to minus infinity. Okay, so this is another nice feature of these coordinates. How is this potential defined? Basically, we require that x0 is the location of the maximum of the Regge-Wheeler potential. So then we can say that V0 is the Regge-Wheeler potential, it was still there, computed at x0, and then alpha can be determined by requiring that the second derivatives are the same at the maximum, and is given by the following expression. Okay, so this will be very complex constants for the generic case, but if you take an expansion with k large, the angular momentum large, they become fairly simple, but I won't need them, so I won't write them. Now we can continue here. Okay, another important feature of this Poisson-Teller potential is that if we perform the following change of variables, so 1 plus 1 divided by 1 plus the exponential of minus 2 alpha, where alpha is defined there, x minus x0, and we redefine the wave function in the following way. So x of xi I omega over 2 alpha times y of psi. The differential equation, which is this one, psi tilde of x, second derivative, plus omega square minus becomes the standard hypergeometric equation. So you will have something like this. The second derivative times psi times 1 minus psi. And then you have c plus a plus b plus 1 times xi, the first derivative with respect to xi, and then you have minus ab y of xi. Okay. Now, I won't go into the details because otherwise it will take too much time, but what one can show is that you have two solutions. So y of xi will be written in terms of C1, 2f1 of A, B, C computed in xi, and then you will have C2, 2f1, another combination of A, B, and C psi. And you can expand this solution at infinity and at minus infinity. Then you can impose the boundary conditions. So we want that when x goes to infinity, since, okay, the drawing is there, since the perturbation we want it to die out at infinity, we have to require that it behaves as a plane wave, an outgoing plane wave. So what happens is that we want that the behavior of the wave function will be e to the I omega x minus x0 at infinity, and an ingoing plane wave when x goes to minus infinity, which it's basically the horizon. Okay, so if you do this, you can put a constraint on the coefficients, and then if you match the solutions into an intermediate region, you find a nice relation for the wave function, which is the following. There will be a constant here, and then you will have e to the I omega x minus x0 divided by some product of gamma function, which I'm not interested in. But the interesting part is this one. You will have also an ingoing behavior. So this is I'm expanding at infinity. So you also have an ingoing behavior here. And you will have gamma of A, gamma of B, and gamma of 1 minus A minus B plus C. Okay. Now, since we want to get rid of this ingoing wave behavior at infinity, we can either ask that 1 over gamma of A or 1 over gamma of B, they go to 0. If you do it for this case, you get some inconsistencies. So basically, if you require one of these, where A and B are defined in this way, alpha squared minus V0 minus 2 I omega divided by 2 alpha. And B is exactly the same, except that there is a minus sign in front of this. Okay, so it's just alpha already. Of this square root. Okay, so if you impose these relations, here you have to ask that A is a negative integer, or here you have to ask that B is a negative integer, and you get this expression for, you get a quantization rule for the frequency, which we call omega extracted by replacing the potential with the potential potential, which is basically plus or minus the square root of V0 minus alpha squared over 4 minus I alpha n plus 1 alpha. Okay, so now these plus and minus are related to A and B. If I choose A, I get the plus. If I choose B, I get the minus, or vice versa maybe. Okay, so it's okay. So since it's in front of the real part, this combination is real. So this is in front of the real part of the frequencies. We don't really care about the sign because it's just meaning that the wave is.
Sorry, can I ask a question?
Yeah, sure.
So, do you understand? So, what you have done so far, if I understand correctly, is you started from the Schwarzschild black hole. You studied spherically symmetric perturbations.
Yes.
And through a series of changes of coordinates, essentially,
yeah.
you have now determined the form of these, the exact form of this perturbation with the appropriate boundary conditions. Is that correct?
I mean, in the meanwhile, I replaced with the correct potential with a simpler one, which is very, very similar. In fact, if you draw a picture of it, and you put 0 here at some place, they will behave like this. They will go to 0 at, this is x, at going infinity or minus infinity. And so if this is the Regge-Wheeler potential, the Poisson-Teller potential will be very, very similar. Okay? So
sorry,
and you can
I thought that that was a result of a change of coordinates. It was not. It was an approximation.
No. The Regge-Wheeler potential here, if you perform this change of variables, since this, it's not easy to invert this change of variables, if you perform the change of variables, you get this v tilde of Regge-Wheeler computed in x, which is very, very complicated. So what you can do is replace it with a simpler potential, which has exactly the same form. Like
okay, so it's at this point you are doing something a little bit more qualitative rather than quantitative.
It's just in order to extract analytic expression for the quasi-normal frequencies.
Okay, thanks.
Okay, so here...
Can you also repeat how you arrived to a quantized form for the frequency? What was the physical requirement?
Okay, so this is the reasoning. Once I arrive to an hypergeometric equation, I can find the solutions. Then I can expand them at infinity and near the horizon, which are special regimes for this variable psi. I can impose the boundary conditions of having only the ingoing wave at the horizon. Then if I impose also the matching of the solutions into an intermediate region, I get another relation for the wave equation, which tells me that I need to get rid of the ingoing behavior at infinity. Hence, one of these two terms must diverge, which is this. Since gamma of A or B diverge when their argument is an integer, this gives me a quantization condition for the frequency.
So is it, am I correct to understand that this potential you does not Einstein's equation?
No, I don't think so. No, I mean, because basically, as I didn't show you directly, but in order to get the Regge-Wheeler potential here, you basically are separating this box acting on phi, and you have the metric. Okay, so from this point of view, it's very easy to say that these potentials satisfy Einstein's equations. For the Poisson-Teller potential, I cannot, since it's a little bit peculiar because it's in terms of a hyperbolic cosine, I cannot see directly the metric that would provide such a potential, but maybe it solves Einstein's. Well, I never tried, so I'm not sure about it. Okay. Maybe one can try to construct a metric which gives that potential, but I'm not sure that you can do that. Okay.
I'm sorry, I'm not understanding something very basic, probably. In which sense this is a perturbation of the black hole solution? This seems to me Klein-Gordon equation of scalar field on fixed background.
On more rigorous terms, you can study linear perturbations of the metric. So you can say that the metric, the real metric G mu will be the black hole metric plus H mu. Okay? Then you plug these into Einstein's equations, expand with h small, and then you can use what is called the Newman-Penrose formalism to decompose the perturbation of the metric into the trace part and also spin 1 and 2. And the scalar perturbation satisfies exactly box of phi equal to 0.
Okay, so phi is the scalar part of
It's
H.
the trace part of the
okay,
perturbation.
Okay, so the stupid question.
No, I didn't want to go too much into details. Because
Would these all fall true if you consider rotating black holes?
if, rotating black holes?
Yes.
Yes. I mean, the problematic part, if they're only rotating, yes. If they're also charged, it becomes a little bit more complicated. But yes, you can do it.
But you can do, you still have the separation?
Because the charge, you can still do it, you can still separate the equations, but they will be much more complicated because the spin 1 and spin 2 parts of the perturbation will couple to the gauge field. So you cannot separate the equations for the gauge field and the equations for the perturbation of the metric. For the scalar perturbation, you can still do that, though.
Okay, so you have a problem if you consider Kerr-Newman, but not if you have
If you
Kerr.
consider scalar perturbations, it's fine. But if you want to study, because for the case of the Schwarzschild black hole, considering the more general case of spin 1 and 2 perturbations of the metric, only means that you are replacing this with a little bit different expression, depending on the spin of the field. Like, then here you will have, I have it, I already done in the notes. I don't remember by heart, but I can tell you what it is. Okay, so I already got this part wrong. So the Regge-Wheeler potential for a generic perturbation of the metric, for a generic component of the perturbation of the metric, will be this one, where S is the spin of the perturbation. So if S is equal to 0, you recover the differential equation for the scalar field. If S is equal to 1, you get the equation for the spin 1 component of the perturbation, and if S is equal to 2, you get the differential equation. But you can do this only for Schwarzschild, I think, not for Kerr-Newman.
Yeah, that's what I was
Definitely
asking.
not for Kerr-Newman, because of the problem with the charge of the black hole. So the spin 1 and spin 2 components will couple to the perturbations of the gauge field, with the gauge field. Okay. Okay, if there are, okay. Thanks for the questions, by the way. Okay. Now, we arrive to a quantization relation for the quasi-normal frequency, what we call quasi-normal frequencies. Now, another interesting thing I want to discuss, yeah, I will erase the first blackboard. Briefly discuss the iconal limit of the scalar perturbation. Okay, so in the iconal limit, we are considering large momenta, so basically K is very large. And what happens is that with this assumption, you're basically saying that the wave function will vary much more rapidly than the geometry it is traveling across. So you can neglect the derivatives of the metric when you study box of phi. And you get this equation. Which I can think as the Hamiltonian of the system acting on phi if I define p mu as a derivative. Okay. Okay. If I do this, since the Hamiltonian can be separated in this nice way for this case, sorry, this is an R plus G theta theta P theta you can directly separate the differential equations, and they are already into in canonical form. So you are acting with this on phi, and you will have two differential equations in canonical form. Okay, so now what happens is that this I want to draw a plot. So this, I will focus on the radial differential equation, okay? So the Q bar of R will diverge when R is equal to M, which is the horizon. And then depending on, this is 1, depending on the choice of the ratio between the energy and the angular momentum, which is basically the impact parameter. If you have an incoming particle, you can see the impact parameter as the ratio between the angular momentum and the energy. Okay, so what happens is that I can use a WKB expansion here. And you can see that I will have, in general, 3 regions. Sorry, this is Q bar of R, the Q value of the radial differential equations into canonical form. And I can use the following ansatz for the wave function. Where phi of R is generalized momentum. Okay. Okay. Now, if I impose matching conditions into these in these regions, basically I can recover the Bose-Sommerfeld quantization condition. So if I call this location here, let me draw a little arrow here. I will call this location here R1, and this location here, I can call it R2. I have that the integral between R1 and R2 of the square root of Q bar of R in dr will be pi times n plus 1/2. And here, okay, so now I can see this as an integral over a contour, and I can make a connection with the Seiberg-Witten differential. Okay. So what I can say is that, okay, because as Dario showed you before, in the case of Seiberg-Witten, you can you can find a differential equation. And if you with in the WKB limit, so when h bar is going to 0, yes, the square root of q Seiberg-Witten of y dy will precisely become the Seiberg-Witten differential. Do you remember, okay, this part? Is it clear? Are there any questions? Okay, there are no questions. Okay, so now, okay, so this is the connection between the Bohr-Sommerfeld quantization condition and the shrinking of the cycles in the Seiberg-Witten language. Okay. Okay, just a little detail. Yes.
At this stage, you don't know whether this is an accident, right?
No.
Yeah. So at this stage, you don't know whether this is an accident.
No, we don't know.
I mean, they just have the same differential equation,
yes,
but they might not have any relation in physics.
Yes, I mean,
okay.
I just found two second-order differential equations, and
which look the same.
And then mapped them into the One of them describes the black hole perturbation, and the other one describes the quantum Seiberg-Witten curve.
Well, I think at the moment it looks like a coincidence, but I guess the connection goes over to other aspects, and then one hopes that there is some physics behind. I think that this is the hope.
So now, I mean, my aim now is to show you how to relate these two systems, and then I will show you two simple cases in which I can understand which cycle is shrinking here, because I don't know here whether the correct cycle is A or AD, because there are, since it's a torus geometry, there are two cycles, A and AD, and one of them is shrinking. Okay, so just a little detail concerning the Schwarzschild black hole. If I take okay, from this equation, if I consider if I expand Q bar of R around its minimum here, I can get these two relations. So I will call it En because I know that it is quantized due to the Bohr-Sommerfeld quantization condition, and then I will have Q bar of R computed in R0 and En divided by the square root of the second derivative. And this will be pi okay, so the nice thing is that I can find this precisely. So I can find that R0 is 3m, and then En is equal to k times this is in the Icon limit. And I mean, I won't talk about the geodesic structures of these geometries, but basically I wanted to say that these quantities that you can see here, you can find them by studying the null geodesic structure of these geometries. So for example, R0 would be the, okay, if I perform a scattering process into a black hole geometry, there will be some specific impact parameter that will lead me to a closed orbit for the photon, which is called the photon sphere. And it will be located at 3m. And also, the radial velocity in the neighborhood of this closed orbit will be like this, where lambda is an instability coefficient that we also call the Lyapunov exponent, and it's precisely, and it's 1 over 6 square root of 3 m. So basically what you find here is 2 lambda, and this is not a coincidence. You can use a geodesic approximation and find these quantities here and have a guess for the quasi-normal frequency directly. And the radial part will be given by the angular velocity of the particle around the black hole, which will give you exactly this. Okay, after this comment, I can start talking about the connection with the Seiberg-Witten. Oh, sorry. No, sorry. I call lambda Seiberg. I put this. Let me call this E, lambda E, because we call them Lyapunov exponent. Sorry. Okay, now, so as Dario said before, you can bring the quantum Seiberg-Witten curve, you can represent it as a differential equation of the second order, and bring it to canonical form. What I will do now is to show you that you can do that. You can map this Q value from the Seiberg-Witten point of view with the, say, Q value obtained from the Schwarzschild black hole. So for the Schwarzschild black hole, you can write Q of R in this somewhat lengthy way, but that will be, there is a 4 here, and then there is 4. A slightly more length long term. I mean, this Q can be written in a more more simple way, but I need this expression because now I can map this into the Q value of Seiberg and of an n equals 2 SU2 super Young-Mills theory with 3 flavors, which I denote NF equal to 1, 2. Why this peculiar way of writing? Because I'm referring to the classical Seiberg-Witten curve, which was defined using this. In the general case with flavor was defined in this way. And now P left will be x minus m3, and P right will be x minus m1 times x minus m2. Okay, so I can map the Schwarzschild black hole, the differential equation for the scalar perturbation of a Schwarzschild black hole into this, the quantum Seiberg-Witten curve of this theory. And what I get for QSW is this. 1 over 4 h bar squared, h bar squared. So let me mention that this was originally done by Albagrassi and collaborators. Yeah. I will write, sorry, q squared plus 2q times h bar, sorry, minus m1 minus m2 minus 2 m3, 1 plus y. And then I'm missing plus 2 m1 squared plus m2 squared minus 4u minus h bar squared. And all of this will be divided by y times 1 plus y. So why did I write all of this? Because now you can, you can, after performing a change of variables, so what you do when you arrive at this point, okay, you have the two q values for the equations. You look at the singularity structure. So here you can see that the singularities are in 0, RH, and infinity. And here you can see that the singularities are in 0, infinity, and y equals to minus 1. So if you perform the following change of variables, okay, I can map the singularities of the two q values of the differential equations in canonical form. And basically, I can use a well-known relation, which is the Schwarzian derivative, which I can write down if you want, but where is it? It's here. Okay. So now I can say that QR of R will be equal to Q Seiberg-Witten computed in Y of R. Then there will be the derivative of Y with respect to R squared, and then there will be some higher order terms, some terms depending on higher order derivatives of Y. But since in this case it's just a rescaling of the variable, I don't need to write them. Okay, and then once I perform this rescaling, there will appear basically, so this will just be y of r times RH squared. And you can see easily, for example, that from here, you can relate these two terms. And you can see, for example, that M1 must be equal to M2. And you can go on and find the appropriate dictionary between the gauge theory quantities and the gravity quantities, which is, in the case of the Schwarzschild black hole, very simple. Basically, you have Q over H bar is equal to minus 2 I omega RH. Then you have that all the masses are equal to okay, again, when you find the dictionary between these two quantities, since there are some square roots, you can find some signs that go around, but I chose one specific dictionary. And your H bar will be k squared plus 1/2 I omega RH squared minus 4 omega squared RH squared. So this will be the radial dictionary for the Schwarzschild black hole.
So, sorry, so the Q over H bar and M over H bar are the same thing, basically? Or?
Yeah, in this case, yes.
So then it means that
From the
in the gauge theory side, there is a relation between Q and M?
Yes. I don't know precisely what this entails into, when you consider the gauge theory side. That the masses of the hypers can be related to the confinement scale, basically, no? This probably has some,
okay, so you
could
don't
be
know
relevant from the gauge theory point of view. But I don't know what happens there in that point.
So how many fundamental hypers you have
3.
here? 3. All of the 3? Everyone has the same?
All of them has the same value, yes. Yeah.
Okay.
Okay.
Can I ask you one thing? At some point you said about the QR that has a singularity for R equals 0, right? also.
Yes.
But I thought that all your matching procedures and so on, you didn't, so R equals 0 would be in the Schwarzschild coordinate, the singularity of the black hole, right?
Yes.
Because the horizon is at 2m.
Yes.
I thought that you imposed all the matching condition. I mean, you didn't care what happens inside the horizon.
Yeah.
But here it seems that there is still some remnant of the information of
Yeah,
singularity
actually,
somehow.
Well, actually, when we study these black hole perturbations, we expect that once they cross the horizon, nothing can come back. So basically, yeah. But in the differential equations, you can still see that there is a singularity. But for example, when you have Kerr black holes, no, so the Q value for the Kerr black holes will still have a fourth order polynomial in R in the numerator, but then here you will have R minus R plus times R minus, which are now the two horizons. Yeah. So yeah, I agree that it's rather peculiar that you still can see the black hole singularity as a singularity of your differential equation, and this, in principle, could mean that you can retrieve some information about what happens inside the black hole. But I mean, we didn't explore that. Yes. We don't care about that, no. I mean, I just need this to find the proper matching for the coordinates. Oh, yes, sure.
So, on the gauge theory side, we have your H bar, which
Yes.
is the omega background.
Yeah,
parameter.
H1, epsilon 1 equals to
Yeah,
H
yeah,
bar.
okay,
And,
okay.
okay.
What's the counterpart on the gravitational side?
As you can see from the dictionary here, I mean, I put all the gauge theory parameters on the left and all the gravity parameters on the right. There is no scale you can match to H bar. It's basically adimensionalizing the gauge theory coefficients, parameters.
So there's no corresponding scale on the.
There's no parameter in the gravity side that you can match to H bar.
Ah, okay.
Because you can always rescale the. I mean, as you can see.
The classical limit on the gauge theory side corresponds to something.
When H bar goes to
meaningful?
0, and when H bar goes to 0, basically it's the WKB limit.
In the gravitational side.
In the gravity side, yeah, you can think that is the WKB, is the iconal, is the WKB limit of this. I mean, you can neglect the. Okay, when H bar goes to 0 here, you are allowed to use the WKB limit in this differential equation. Okay. In order to use the WKB limit in this differential equation, you need to take the iconal limit. So you have to consider the momenta to be large. So basically what I was saying is that the H bar goes to 0 can be related to the iconal limit. And I can tell you more because K is basically the angular momentum divided by H bar, gravity H bar, okay, if you want. So you can see the iconal limit in that way. Okay.
The question is, was this supposed to work only in the iconal limit? So my question is whether you can really say all this by always assuming K to be very large, because when K is very large, then you can match this kind of a structure of.
No, you can do that also when K is not large. I mean, the differential equations can be mapped consistently also when K is not large. So what happens is when K is large.
You did drop some terms in the differential equation because
yes,
of the
and basically you can see that
So I say in the derivation of QR, so K is totally general. It's not
Yeah.
really okay. Didn't take okay. Okay, thanks.
Yeah, I mean, you can see it from here, no? There's a 1 plus 2 K
Yeah,
squared.
exactly. I was thinking always in mind that K was large, but okay.
No,
it's not.
sorry, maybe I confused you because first I talked about the diagonal limit and then I
Right.
switched to the general case.
Okay, right. Okay.
So maybe I confused.
No, sounds good.
Yeah, sorry. Now everything is general now for the Schwarzschild black hole. Okay. Sure.
So, I mean, just to understand this last point, so this mapping is valid beyond the Eikonal limit?
Yes, it's
which
it's always
on
valid.
the Seiberg-Witten side, what does it mean? That you don't have to take h bar to 0?
Yes.
Okay, but then, I mean, isn't there, so, I mean, very loosely speaking, the non-Eikonal limit in the black hole perturbation theory is still classical, right? Like, I mean, it's a classical theory.
Yeah.
So how should I interpret this? I mean,
you are taking. I mean, you're studying the wave equation, so in some sense it's quantum. Yeah, it's classical because there is no h bar, but yeah, in some way you are considering waves scattering in the geometry. Hmm? Yeah, they are classical because they solve the Einstein's equation. Yes, yes.
But so the mapping really is between like the fully classical black hole perturbation theory and the fully quantum Seiberg-Witten curve.
Exactly,
okay.
Yes.
Sorry.
Yes.
Thanks.
Okay. Okay, can I go on? Okay. Yeah. Okay, so now that I told you about the Schwarzschild dictionary, the dictionary for the radial equation in the Schwarzschild black hole, I want to describe what happens if we consider Kerr or Kerr-Newman black holes. So I will only write down the dictionary. I will start with the angular equation. Okay, so we will, again, for the Kerr-Newman black hole, what happens is that aside from the mass m, we will also have the black hole rotational parameter aj, which is basically its angular momentum divided by the mass. And then we will also have, in principle, a charge, which I define as calligraphy q. And again, I can separate the differential equations for the scalar perturbation and find, again, this. And also for the angular equation, where chi here is the cosine of theta. It's just for simplicity. Okay, now the dictionary for the angular differential equation is as follows. So Q over h bar, Q is equal to over h bar, yes, because it's, so it's again, sorry. Again, I can map both of these differential equations to n and f equal to 1, 2, again. Okay, so the dictionary for the angular part will be as follows. Aj omega, the perturbation of the frequency of the scalar perturbation. Then you will have u over h bar squared. Again, I'm taking k to be generic, also small. Okay, and then the masses. Two of the masses will be 0. And then one of them will be related to the absolute value of the quantum number related to the projection of the angular momentum along the z-axis. Okay, so why I want to study the angular equation now? Because you can see that when aj goes to 0, so I'm retrieving the the spherically differential equation for the angular part, q goes to 0, and also all these terms vanish. But when q goes to 0, we know that the following relation holds between u and a squared, u and a. So when so u of q equal to 0 from the gauge side, we know that is equal to a squared. So I can find a relation for a, which is very interesting. Okay. So what happens now is that if we consider for an instant the iconal limit, as I said you before, in the iconal limit I can use the WKB approximation, and this will give me some relations on q bar of chi, which is basically the same q, but neglecting the constants with respect to k squared. I can find the following equation equal to 0 if I perform the WKB limit, and then I can solve this and find that Kc is equal to 0, and this is basically telling me that theta is equal to pi over 2, so I can focus on the equatorial plane. Since it's spherically symmetric, it doesn't matter, but okay. And also that k squared must be equal to m phi squared, and this is what I expect, because again, it is spherically symmetric, so I can take the angular momentum along the z-axis. Okay. Okay. Now, if I use if I look at this equation and use the dictionary in the case aj goes to 0, what I find is the following. Let me speed up a bit. What I find is the following. So I can say u is just this part here, without the 1 over 4. So a squared is equal to over h bar squared is equal to, let me call this critical because it's in the iconal limit, k squared, which is equal to m phi squared, which in turn is equal to m2 squared over h bar squared. Okay, so I can see that if I consider the following cycle, so I take a minus one of the poles at the masses, and they appear naturally when I introduce flavors into the gauge theory, I can write this as a cycle in the Seiberg-Witten side. And when h bar is going to 0, I can see that this is going to 0 when h bar goes to 0, because if I plug this into this and this into this, I get 0. So what I expect is that when I reinstate h bar, so I'm not in the iconal limit from the gravity side, so all these constants reappear. This will still be the correct cycle because everything is perturbative in aj. So by analytic continuum, I mean, I can think that this is still the correct cycle, so I expect that this should be h bar times n chi plus 1/2. Okay, now the nice thing is that if I now use the same dictionary, so I replace u squared, but if I consider h bar to be small, so, and aj to be quite small again, if I reinstate the constant without performing the iconal limit, I can find, if I retain these constants here and solve this equation, I find the following value for k squared, which if I and chi as L minus the absolute value of M phi is exactly k squared equal to L times L plus 1 with L an integer, a positive integer. So I basically was able to derive the correct eigenvalues for the spherical harmonics. So this is a confirmation that what we are doing makes sense, basically. So the main point behind this is that there are some limits in which, for in this case, when q goes to 0, in which I am able to understand what is the shrinking cycle. Okay, and then by analytic continuation, I can extend this reasoning to more complex cases, which are of more physical significance.
Sorry, 1 second, I'm lost. Because you said that you can do this match when h bar was going to 0, which is not the same thing as q going to 0.
No, they're two separate things.
Okay,
so if I sorry, you're right. You're right. If I reinstate h bar, I can still keep this dictionary and find this.
Yeah. Okay. So you cannot substitute there.
Yeah, no. Okay. No.
Good. That was my question.
Okay. Yes, sure. Okay. Great. Okay. So for the angular equation, we have seen that the cycle is A, and the quantization condition is this one. Now I want to show you specific regime for the radial part, which lets me understand what is the correct cycle to quantize in the for the radial equation. So I will need to write down the radial dictionary.
So Alfredo, how long do you still need?
I'm almost done.
Okay.
Like maybe 6 minutes, something like that.
Sure. Okay.
Okay. So now, if I perform the following change of variables, here R plus and minus are basically these, which are the two horizons of the Kerr-Newman black hole. If I perform this change of variables after bringing the differential equation for the scalar perturbation of the Kerr-Newman black hole into canonical form, I can find the following dictionary, again with an f equal to 1, 2. This is 3. And then we have 2 here over each bar. It's more complicated. While the dictionary for U, it's more lengthy, and maybe, it will take like 1 minute just to write it, so I will skip it. If you, the notes will be available, so if you need any details, you can ask me afterwards, or you can see the notes. But I won't need the U part for this case, so.
So
okay.
I think so. All the quantities you are writing are dimensionless, right? Because
yes.
h bar
as length,
as
dimension
dimension of a mass 1, no?
Yes.
Despite the fact it's an h bar, but it comes from the omega background.
Yes. So yeah, on the left, they are they're all the dimensional, these relations. Okay, so why is it interesting to study also the Kerr-Newman black hole? It's not just more complicated per se. Because there are some interesting things happening. So for example, when Q goes to 0, so Q goes to 0 either when omega goes to 0 or when the two horizons coalesce. When the two horizons coalesce, one of the masses is diverging, okay? And this is very interesting from the gauge side, gauge theory side, because you can see that the product Q times M2 is kept finite. And this is exactly the decoupling limit for the second mass of the theory. And this will define a new scale, Q tilde. And I will flow into a theory with NF equals to 1, 1. Okay? So for the extremal Kerr-Newman black hole, I need another quantum Seiberg-Witten curve, and I can match them. Or I can use I can redefine Q tilde in this way, and also redefine psi tilde. Why I need to redefine, y tilde? You can see that when the two horizons coalesce, also y is diverging. Okay, so you can see it from there. But if you do this, you find. If you use these relations, you find exactly what you would have found by starting again from the NF equals to 1, 1 theory, and you get the extremal Kerr-Newman black hole. And this is a general thing. When a black hole, also in 5 dimensions, when they become extremal, you will lose one of the flavors. Okay, now Q is going to 0, and M is diverging. But what happens if I set one of these parameters here so that M2 is kept finite? So if I do that, if I choose a value for omega, which is keeping this ratio finite, I find a very interesting set of modes, which are called super radiant modes. So if you want, this is one of the nice features of this language, because here, just by investigating a very, simple idea from the gauge side, so Q is going to 0, I found a very special regime in the black hole, for the black hole, which is this super radiance. So what happens, as you can see, these modes here, they lack the imaginary part, which means that will not be damped, okay? And they basically correspond to the extraction of energy from extremal rotating black holes, okay? So there is a constant flow of energy going out of the black hole. Okay, now...
And what is the gauge theory limit where you recover?
Q goes to 0, and then all the 3 masses are different from 0. And then you're not decoupling M2 anymore. So M2 is finite, M1, M3 are finite.
So what does it mean Q going mass scale, no? So
yeah.
it goes, it is much bigger than what?
If you want M1, M3, and M2, they're going to infinity with respect to Q. Something like that, yes.
You don't do anything with H bar?
Hmm?
You don't do anything with H bar?
No.
So it is Q much smaller than any fundamental mass scale of the theory.
That's basically it. Okay. Okay, so I can do more. I can study near super radiant modes. Where delta, for simply, I will call delta the difference between the two horizons of the Kerr-Newman black hole. Okay, now you can follow the following. You can use the following reasoning and study the radial equation in two limits. So the first limit will be R much larger than R plus, which is much larger than delta. And I will denote this so what you can see from in this limit, since R is much larger than R plus, and since the structure of Q R is some polynomial of R squared, from this point of view, these singularities will coalesce. And interestingly enough, by setting omega equal to omega plus this, the point at infinity will become singular regular, not irregular anymore. So I will have at infinity, R goes to infinity will be a singular regular point, and R goes to R plus will be a singular irregular point. So basically this equation here, in this regime, will be described by a confluent hypergeometric. Then I can study the other regime, the one near to the two horizons. So I can define R to be R plus. So I'm near the two horizon, the external horizon. Then I can put a variable tau here times delta, which is the difference between the locations of the two horizons. So when tau is small, what happens is that I'm able to resolve the two horizons even though R minus is going to R plus. Okay, so if I'm very near to very close to the external horizons, even when they are coalescing, I can still see a difference. But again, the point at infinity will be singular regular. So I will have three singular regular points, and this equation will be described by a standard hypergeometric. Okay. Now I can do what I did in the beginning for the Schwarzschild black hole and impose the boundary conditions, the outgoing wave boundary condition at infinity and ingoing wave boundary condition at the horizon. This will give me a relation between the coefficients of the solutions computed in this regime and the solutions computed in this regime. I can then match the two solutions into an intermediate region and find the following condition, which is very interesting. So there's a squared here, and a squared here, and there is B bar, and then there is gamma of C bar minus A bar squared. And this will be equal to 1. Now, who are these guys? These A, B, and C bar. They will be the coefficients defining the hypergeometric function here. And they have an expression. So for A bar, I have 1 over 2 minus alpha minus 2i j and nu times omega divided by omega phi 2i r plus omega super radians. For B bar, I will find an analogous expression with this with alpha changed of sign. Sorry. And then this will be the same. And C bar will be 1 minus 2i aj nu divided by omega phi, and I'm still missing something, which is alpha. Alpha is this relation here. I mean, you can easily derive all of these relations by looking at the equations, and it is done on the notes, but it would be very lengthy to do it on the blackboard. So what I want to say is that alpha has a small real part, because you can see that typically this part is bigger than this, but k is complex because the separation constant now, because now the black hole is not spherically symmetric anymore. So what happens is that also the separation constant gets an imaginary part, and this will lead to a small real part for alpha. Why I need this analysis? Because here now I can see that when delta is going to 0, this quantity will diverge. Since this quantity is diverging, I need that this quantity has to diverge. So again, similarly to the Pochler-Teller potential for the Schwarzschild black hole, I find some kind of analytic expression for these near superradiant modes. I'm almost done. Because now I can rewrite that relation in terms of gauge quantities. So if I do that, if I rewrite the relation, this relation in terms of gauge quantities, what I find is that minus q over h bar at the power to the square root of u over h bar square root of u over h bar I goes from 1 to 3, and then I have these gammas here, 1 over 2. Oh, this is a plus, sorry. This is equal to 1, but so this is basically the logarithm of the derivative of the one loop part of the Nekrasov-Shataishvili prepotential. This is basically the logarithm of the derivative with respect to A of the 3-level part of the Nekrasov-Shataishvili prepotential. So basically what I wrote here is just e to the since AD is the derivative of the prepotential with respect to A, and since this must be equal to 1, I can see that AD must be equal to h bar times some integer nr. And that is it, because now I can see that in this superradiance case, when q is going to 0, okay, there, the shrinking cycle is AD, but then if I consider R plus and R minus to be different, I mean that is perturbative in the difference between R plus and R minus, so I can expect that this is the correct cycle also when I'm not in the near superradiant regime. And this is what we use to compute the quasi-normal modes for the generic Kerr-Newman black hole. And you can see that it still holds and it still works when the black hole is not near extremal. Okay, so that's it for me.
Alfredo? So now we have about, say, 20 minutes, because we started a bit late. So let's start the discussion with Andrea.
Okay, so okay, so maybe this is a bit simple-minded as a question, but if in the gauge theory side I tweak the lambda and the masses to get the Argyres-Douglas fixed point, what do I get in the black hole?
Okay, so that is something we always wanted to do, but we never get to do that actually. But in the Argyres-Douglas point, we expect it should be near one of the singular points of the moduli space. No? So at the beginning, we were thinking about considering the gravitational problem with parameters which are close to the photosphere of the black hole. But then we realized that that's not the case. So I don't have an answer for your question, but I mean, we thought a little bit about that. It's a very interesting question. Thanks for asking. But yeah.
Thanks.
I mean, it's a topic. If you want to explore that, maybe if you want, I would be glad to hear.
Very nice talk. I have a comment on this, and I realize it might be seen as a bit provocative, so I really beg you to not take it in this way. I'm just trying to understand.
Okay.
So I wanted to propose the following case. Compare these two systems. One is a mass attached to a spring with some damping force, and the other is the RLC current, the circuit. It just happens that they satisfy exactly the same differential equation,
Yes.
and because of this one can make a beautiful dictionary between the quantities, like the inductance is the spring constant and so on.
Yeah.
In which sense this is somehow different from what you're proposing? Like in the example I'm considering, I don't see any deep physical reason for which I should compare an RLC circuit with a spring with a mass. It just happens that they have the same differential equation.
Okay, so there are two arguments for this.
Thank you.
One of them requires a new ingredient which we didn't have time to introduce, which is the AGT correspondence. The AGT correspondence relates two-dimensional CFTs, Liouville theories or Toda field theories, to supersymmetric theories such as the SU2, Seiberg-Witten. Okay, but then these two-dimensional CFT can be related to some string models using some dualities. So that would be one venue to follow, one way to follow, and try to understand if there is something more physical about this. And then also there is another thing we didn't have time to introduce, which is the brain picture. You can write down a cartoon, you can write down to describe these theories, which is basically you can take NS5 brains, okay, and then suspend D4 brains between them. So what happens is that positioning these two NS5 brains will effectively compactify one of the dimensions, basically. And this will give you a four-dimensional field theory, which is the, in this case, would be the U2 or SU2 gauge theory we were discussing before. And also you can add D4 Fravor brains. Okay. And okay, so this picture is useful to understand what happens in the Seiberg-Witten language, because the distance between, so this will be related to A, the value of the scalar field, and the distance between the flavor brains and the brain will be the masses of the hypers. Okay, but that's not the whole thing, because you can also give a description of this in terms of M5 brains wrapping a Calabi-Yau, and then the classical Seiberg-Witten curve would be could be a cycle. I mean, this is not. I mean, from the classical point of view, okay, it should be a cycle wrapping this Calabi-Yau threefold. And also, so this is a way to relate. So basically, with M5 brains, you can also construct some black holes. So if you do that, so if you construct, I don't know, 3 charged black holes, I think, with M5 brains, and also use them to describe the gauge theory, you should be able to find a more physical relation between these two systems, the black hole and the gauge theory. This, I mean, this is a proposal; it's not something we did. So the idea is to study. Sorry, just to finish, is to study the M5 description of this theory here, and then also the M5 description of some black hole theory. And at that point, you can see the physical relation between the two systems, the black hole and the. But we still have. I mean, this is a proposal, basically.
Federico, devi usare.
This is very satisfying. So you're saying there is a reason for which this is more than a coincidence, because I can get the gauge theory with some like an Witten cartoon or brain engineering, and then I can also see the brain as like some superiority solution that will give me the black hole, and you connect them in this way, basically.
I mean, yeah, but we haven't done this yet because it's not so trivial. But that is what we expect.
The idea, okay.
Yeah.
Thank you very much.
Also, the other very interesting idea is to study the relation with the conformal field theory and then directly string theory. I think that's a way more interesting topic. Yes.
Just a quick question. So in the anterior setup, can you turn on the omega background parameter?
Yeah, I'm not sure about. I mean, I'm not expert enough in this field, so I don't want to say some imprecise things. But you should be able to do that. But yeah, I don't. I mean, I don't know. I will be honest, but it's out of my expertise right now.
I just want to make on the question you asked. Even I think there is something striking about this problem, which is the following: these people that study, the quasi-normal modes, they come to this equation and they do numerics basically, and they compute these things. So, okay, if you're happy with numerics, that's it. There's nothing deeper to find, But in this way, you are like, first space it's quite normal because the techniques for the class of Shataishvili are very advanced. And you get impressive precision, and it's a first principle. It's striking. Even if it was a complete accident, we now have a way that is completely analytical to compute this coefficient. So that's valuable on its own. It doesn't have a string derivation. No, but the point is that even if it's a striking coincidence, it's just amazing. So it doesn't have.
Yeah, it's still very useful. Only, yes.
So, are you saying that the techniques for Negatov-Shataishvili are more advanced than the ones of RC circuits? Certainly.
Okay.
So this was all for scalar perturbations, right?
Yeah.
Does this generalize to non-scalar perturbations?
It depends.
Okay. I mean, I don't care about charge, so let's just take curved black hole. And I mean, in particular, I'm thinking of the Tucholsky equation, which was supposed to describe gravitational perturbations.
You can do that also for the Tucholsky equation. Yes.
I mean, very, very naive question. What happens to the extra indices, basically?
Because you're introducing more like the
tensor perturbation and stuff like that.
Okay, I don't remember now the dictionary precisely because we focused on the scalar perturbation, so we always choose a specific value for the parameters giving you the. But I think they just enter in the. They will just enter in some ways into the dictionary you already have. There won't be a new. You won't. I mean. In general, you won't need a different theory to describe that, in general.
So you're saying it has been done anyway?
Yeah.
Okay.
We also did it for the, again, the scalar perturbation of the ADS Kerr-Newman black hole.
Right.
A specific scalar perturbation with specific mass. So, yeah.
Okay, thanks.
I think the first is a comment for the black hole thing. I guess the problem with the brain construction for Schwarzschild and Kerr, I think, is very well known that you should introduce some anti-brains thing. But I think you have also models for which you have, I don't know, micro geometries or J-Mart solution, also simple D3 brain where this can be done. I think one can check. In that case, you don't have to use M5. I mean, in the black hole picture, I think large supergravity regime, I think you can also use normal like brain ingredients. And have to
yes, okay, but I mean, so the main point I was trying to make is that this picture here you can rewrite it in terms of M5. Yeah. If you can also construct a black hole out of M5 brains, you could find a direct relation between the two theories.
The other thing is a question is about thermodynamical properties of your solution. Do they have some meaning in the field theory? Some like shouldn't be complicated, I guess. Some like the area of the horizon or something that should be encoded into the theory, and whether this can be somehow helpful if you take some conformal limit of the theory, blah blah. Then so from some microset counting or this. Kind of thing.
This is a very very interesting question. And so, what happens? For example, in the case of the super radiant modes, is that the leading correction is as follows. I have an expression here. It's very easy, but I don't want to get it wrong, so I'm just copying it up. Actually, it was here, maybe. Okay, it's here, sorry. Okay. So the real part, we get a correction which is proportional to the black hole temperature. And also the imaginary part will be proportional to the black hole temperature. So now in this case, maybe we are cheating a little bit because the black hole temperature is proportional to the distance between the horizons. So we are just saying that when the temperature of the black hole is going to 0, Q is going to 0. But what you say is very interesting, actually. We actually didn't check if some quantities, thermodynamical quantities of the black hole, what is their expression in terms of the dictionary here, of the gauge theory.
So for some system, you have microscopic descriptions of exactly what happens.
Yes,
maybe it can be related to the
string. Yeah, but you can construct an expression using the dictionary, and then maybe there are some interesting limits in the gauge theory that correspond to.
Yeah. Thank you.
Thanks for the question, which was very, very interesting. Yes.
More questions? If not, before thanking the two speakers, Alessandro needs to make an announcement.
Okay. Yeah, just a couple of quick things. So there will be first a gong show and then a poster session after lunch. So if you are presenting a poster and you have your slides to present in the gong show, you are supposed to have sent us already the slides. So if you did not do that, do it right away so that we can put them on the computer and prepare the gong show. And you can put on the posters. You see the boards there. You can just pick a board and put on the posters during the lunch break. Then for everybody else, in a moment we will go to lunch. There are 23 seats in the dining room. They are already put in a checkboard pattern. You're supposed to go there and sit down where the chair is. You're not supposed to take all the chairs to one table and make a big party. Please note that we are more than 23. In fact, we are basically 46, I think, if we counted right, which means that essentially half of us will have lunch immediately and half of us will just wait a little bit and just, you know, pick your half and be patient. Everybody will get food. There is plenty of time. Just have a chat with your friends before if you don't fit in the first round. Sorry for the housekeeping again.
And let's thank Dario and Alfredo.